So it's kind of neat. It's the first conference where I was driving to the conference and listening to you guys on Zoom on my way along the 401. See? So north of you. So it's sort of about explaining why reservoir computing works to my satisfaction. Upstate New York, that's Potsdam, there's Clarkson, and it's Clarkson Center for Complex System Science. I'm Erik Bollt, and it's bits from three talks, three papers. One was the upper right about explaining how reservoir computing works. There's a connection to NVAR, to nonlinear vector autoregression. Then about a year later, Dan Gothi and I souped up what was a demonstration in the first paper and made a practical method out of it. We call NGRC, next generation reservoir computing, because of an equivalence to the NVAR. And then the last one, I ended up cutting most of it out of the talk, but it's still related a bit to the talk, which is a random version of DMD actually through Johnson-Lindenstrass theorem, and there's a connection to that. Okay, so what's reservoir computer? Okay, it's late in the conference, first day, and everyone talked about reservoir computing, so I'm not going to do much introduction. But it's a neural net method for forecasting dynamical systems. It's a kind of recurrent neural network, and it's one where you don't bother training most of it. You just train the output layer. So it's clear it should work. It's clear it should work quickly. It's not clear that it should work well. So it's a surprise to me it works well, and even now that I've kind of had the hang of it, it's still a surprise to me it works well, but it works fantastically well. So citing to 2001, 2004 with Jaeger and the Jaeger-Haas is where the idea came from. I'm getting used to this. So the kind of punchline you would get is, you give it everyone, oh, I hit the wrong buttons. You give it some kind of dynamical system data. It's more exciting when you give it chaotic dynamical system data. So the Lorentz equations. On the left is ground truth data. In the training stages, it fits so well that the training fits on top of the true data. You see no difference. So the red on top of the blue. In testing phase, it works quite well over several Lyapunov times until you start seeing some divergence. The part that's really, really surprising to many of us is that once it starts making errors, it starts making good errors. So the kind of errors where I've heard it called, it predicts the climate. Or in mathy terms, you'll say that it starts reproducing the invariant measure. So it makes plausible errors. So it's simple. It's much less data hungry. It requires very few parameters at the end of the day, but they are critical. And it's flexible in your features, it turns out. Okay, wrong way. Nope, I'm an amateur with the buttons. As it turns out, okay, so it's not a feed-forward neural net. It's a neural net where you essentially have what's called the reservoir. You have self loops in the middle layer, and all the weights in the middle are chosen randomly. So where does the random go? The punchline is that time soaks up the random. And I'm going to show an equivalence to NVARs. It's a logical bridge to something else from econometrics. And with that, you get something called Bollt theorem. This is a slide I should run through super quick because I think everyone did it. So the classic reservoir computer is you feed in data, X, and so the X may be the Lorentz data, X, Y, Z. And then you feed it in by some random weight matrix W into variables U, which are typically high dimensional. So W won't be squared, be typically like 1,000 by 3, and you'll be like 3-dimensional. And then you get an inner variable R, which is the current remembered state of it, that's based on updating your current internal state by an update matrix A that's going to be also, say, 1,000 by 1,000, and that's random weights, plus the input signal, plus a bias of some kind. And then you hit it with some kind of threshold function Q. So typical threshold functions are some kind of sigmoidal shaped function like hyperbolic tangent or the sigmoid function. And there's a lot of ground in my discussion to be made by just choosing identity function and putting the nonlinearity someplace else. So we heard both of these fellows, Gunnan and Ortega, speak today. I've always admired these two papers of theirs from So 2019, 2020 about universal approximation for RC. And one bit in there is that you get a universal approximation even if Q is identity function. So even if you have a linear reservoir, but you do nonlinear readout, so by polynomial readouts. So that's existence, but not necessarily constructive. And all these weights are chosen randomly. All you train is the output by least squares, super cheap. Meanwhile, from a much more classic topic from econometrics has to do with time series forecasting. And this is an example of what's called a VAR, or it could be an R autoregression, but I'm telling you that it's vector valued. It's vector valued. So VAR, vector autoregression, in K steps. K here is, I'm sorry, I'm terrible with my buttons. I'm trying to point and I keep pressing the arrow button. I should practice with one of these sometime. P delays plus noise. So a linear combination of previous values. It turns out that this kind of a setup and autoregression can do a wide range of stochastic process type forecasting. And here's two examples from an R1 and an R2 of what it can produce. What would be nice to know is if I show you a time series, could that time series be created to a high degree of accuracy by an R? And there's a whole Bollt theorem about that. A certain white noise, stationary, bounded processes can do that with R's, autoregression or vector autoregression. So finding a connection to that lets you lead on an old theorem. So let's warm up. So the idea of this discussion is to take the reservoir equation here, which is the internal variable R, and update it with data U. Remember, U was read in data from the X. X reads into the right size U data, and it adds in just as you're updating the internal variable from the previous step by all the weights A and perhaps offset. So this equation. But if Q is identity, it simplifies quite a lot. But anyway, whether you assume that about Q or not, you basically collect all the previous values of R in the internal state, and you'd like to read them out. So the reservoir runs whether I read out the values or not in training phase, and I can just collect them as column vectors. And reading them out means projecting onto the original variable X by some projection matrices I call V. So VR is this arrangement of all this X data to VR data. And the best readout matrix is just meant to be the argument of what I want the X's minus the VRs. So VR means your readout matrix before I've optimized for it. So it's a least squares problem. This is stated in Frobenius norm. So a least squares solution of this would be an expression almost like this one. Everything's kind of backwards because you're right multiplying. The unknowns are on the left, the V. So it's this is essentially the Tychonoff form of ridge regression. So least L2 regularized fitting of the V is the W out. So you need some kind of regularization to prevent overfitting. But anyway, it works quite well. It's still a mystery to why it works. But it does work extremely well, and it's extremely easy to program, as many of you have described here. Here's some data from Lesotho-Mackey equation, which is a differential delay equation. Here is a blow-up of the same, because most chaotic time series, they look kind of Etch-a-Sketch-like, unless you look closely. So this is a blow-up over a shorter time range. Here's the internal variables over the same time range. And in this particular instance, there's 1,000 of them. So I'm only showing you about 20 of them so that it doesn't look like a big blob. So it ends up doing very good forecasting, but I'm not going to change something. I'm going to, instead of, this was done with hyperbolic tangent, I'm just going to drop the extra terms. That's where I started initially, is thinking in terms of approximation with Taylor series. But at the end of the day, I'm going to say it isn't going to be an approximation result. It's just motivated by this. But you look at you look at a hyperbolic tangent, and over a narrow range, it looks kind of like a line. That's obvious. As long as I keep the data bounded somehow, and you keep it bounded by that update matrix A, then it'll stay in that smaller domain. It'll stay in that region where you're mostly like the S part of the hyperbolic tangent. And if it gets large, then you end up in this step part where essentially the thresholding saturates, and you're feeding in ones and minus ones, and they become kind of dead variables to the whatever synchronization process is happening in your reservoir. So that's what motivated that. But once you're motivated by that, the updating scheme is trivial for getting the new R's from the old R's. So the new R, the internal variable, is equal to the old R times A plus the read in variable U. The read in variable U is read in the first variable X. So it's convenient if you choose the initial R to be 0. Choose the initial R to be 0. So this equation just says W in X1. And then the next guy is A, the old R, plus read in the new one. So it's hit A on everybody, and W in X1 is what U2 is. So you end up with this equation with A. And you do it again, and you end up with another A. And you just keep adding in a new term with an A and an A and an A and an A. So it's basically a linear iteration. Just remember, these aren't square matrices. Otherwise, it's quite simple. So after a while, you have a very simple expression. And if you've ever done linear control theory, this starts looking kind of familiar, because I'm going to strip out something that looks a lot like observer matrix from control theory. But anyway, you basically have powers of A times Wn times offset shifts of each of the data value X's as they are read in. And that's the whole story. So manipulating that expression in a few ways does some fun things. So what I'm going to do is I want to build a W out on that rth guy, but that R plus 1th guy. But the R plus 1th guy is this sum over all the previous values, read in the actual natural X data, and hit it with powers of A. That's what's inside this R plus 1. Hit it with the W out. Well, putting all that in again, I basically W out, W in, wrapping around powers of A times X1 through Xk. And that's the whole thing. So once you eyeball this thing, you realize, okay, these are not square matrices, but the W out and the W in are the natural size with the size of the power in there. And these things make square matrices. So each of these guys is a square matrix times the data in turn. A square matrix times the data in turn. So they're like coefficient matrices times the data in succession. Notice I just reversed the order. I put the kth guy. The kth guy is here, so I'm calling this the A1, and I'm calling this the AK, K guy. So that's my definition. Call the AJ guy this in powers of J.
K is fixed.
What's that?
K is fixed.
This K is just the counting number. Yeah, counting on through. So this K, okay, I said ARK earlier, but this K would be whichever one I'm going up to. So this K would go out. So if I'm on the kth step, then it's fixed. On the next step, you've just raised it one. So in a sense, I'm writing as if there's an infinite memory.
Okay, so you keep.
I keep going.
Keep going, you keep your other ones until before. It's not a cutoff.
No, I'm not cutting off yet. I'm going to cut off soon, but not yet. Yeah, my plan is to cut off, but not yet. So this is going to be up through the kth step, having gotten at this point up to K plus 1. And that's the whole story. Now look at this thing. And I said, well, that's a very familiar object. It is basically a var K. Except if I keep going, it would be a var K plus 1 and a var K plus 2. But in principle, I'll show you that said better in a minute, but these A to the J's, they should be shrinking, or they shouldn't be growing if it's going to mean something. And there's your fading memory. So I will truncate shortly. So I'll pause for a second and just dance around this. So this is a var K. Certain stochastic processes have a var, an infinite var representation by Wold theorem, and a good approximation for a large enough k, which this could be. So the fact that this equals a var k is interesting. It's not another thing, it's one and the same, it's just looking at it in a different view with that particular threshold function. Okay, so just bookkeeping and keeping track of data. So that was a star from Econometrics, the var k, but I can arrange my data. Let's say, I'm sorry, my buttons are terrible today. If I take this x1 through xk and I stack them, then I can stack the coefficient matrices A as well. And that's what you do here. Except stacking the coefficient matrices is as a row of matrices, and the stack of xk's is like that. And you do that across all times, and you have all of these multiplications give you all the output vectors as so. So that's the entire statement of data. And if I keep going, in principle, I would have to keep increasing the k, but at some point you might choose to stop adding k and cut it off. That's your question. And you have a reason to do so if these shrink. But now when you look at it like this, then this is the least squares fit in terms of this squiggle x, I call it, the cal x. And what's that?
Blackboard Bollt.
It's like
Blackboard Bollt.
no, \BB, yeah. It's \BB. You know you're geeks when you talk to your audience in LaTeX. Any case, with this expression, I can solve for the W out exactly by remembering that the W out should fit this equation, and you'll observe that A star that fits this guy follows this equation, the best A star. Maybe that's what I want, or maybe I want the W out, which can be written in terms of the A stars. And here's an expression between the W out and the A star. But the W out's just an intermediary. Maybe you shouldn't ever be building your random neural network. Because if they're equivalent to this thing, maybe you should just be skipping that step and thinking in these terms. What would I do if I had it? I would just fill out this expression, and all I really want is the A's. And since all I really want is the A's, then there they are. Just form them directly. They're equivalent. It's the same thing. And also, by the way, this this matrix of W out times A, W in, W, oh, there's a type, W, let me repeat. W in, A times W in, A squared times W in, A to the K minus 2 times W in, all the way to A K minus 1 W in. This is an A matrix. I can think of this as the A matrix, and it's all the stuff which are precursors to this. It's this expression right here, A x squared backslash BB A backslash BB X. They're both built into this expression. That looks a lot like an observer matrix from control theory. Okay, anyway, doing just the linear story, it works pretty well already. You can do pretty good forecasts with it, which is all Wold would have ever promised you, that you do pretty good forecasts for a little while. And it does do pretty good forecasts, but it doesn't do this one thing that's amazing that Reservoir can do, the nonlinear Reservoir can do, which is predict the climate. Once it starts making errors, it starts making good errors. But there's a way to soup it up. Okay, so anyway, this is a punchline so far. Linear RC with linear readout implies an implicit var. And so for every such guy on the left, there is a guy on the right. For every linear RC with a linear readout, there is a var that you can lean on instead. So you may as well just do that. And where do the random projections go? I forgot to tell you that. Where do the random projections go? You're basically, if you inspect this very carefully, and I say this in great detail in my paper, you're essentially projecting out by the columns of A, or in the A space as you go. It's essentially an Arnoldi projection, an Arnoldi iteration. Oh, wrong direction again. Okay, so it already works quite well, but once it starts going bad after a while, this forecast was pretty good on Lorentz up to about here. Up before that was okay. And after that, it starts going bad the wrong way. And the attractor is all messed up. But if I do something else, which is a lot like what I just said, which is instead of doing a linear readout, I do a nonlinear readout. A lot of the analysis I just showed you, it pushes right through, and it does a fantastic job. So it forecasts over many Lyapunov times, and once it starts making errors, it starts making the good errors, just like RC, because it is a kind of RC. It's just another way of doing the same thing. Before I show that, I just want to point out that this thing that kept showing up in my expressions, W out A to powers W in, these are the coefficient matrices, which I'd like to truncate. And this is written in atomic norm, which is an easy norm to work with. But actually, any natural norm, you can do a similar result. But anyway, you get powers in A. Powers in norm of A to powers should be decreasing if the norm of A is less than 1. So you would expect that these coefficient matrices will shrink in time. And sure enough, in practice, they do shrink in time. So for the Lizotte-Mackie problem I showed you, you have a little increase, and then it quickly falls off by around 6. And for Lorentz, it falls off pretty quickly too. So pretty quickly, just ignore them, and it does a good job. Okay, now I boiled this one. This is kind of, I've used versions of these slides a fair bit in the last year and a half, but I keep adding to them, and I keep pulling other ones out so I can say something new. So this is the NVAR stuff all on one slide. I'll say it's almost the same thing that you get out with a lot of technical details that are just algebraic. If instead of training your output on the R values, you also train in powers of R. So this is written as powers of R, but this is Hadamard product, the circle dot. So like RK, Hadamard product, RK. And for the geeks who like to speak MATLAB, that's just the start dot times in MATLAB is the Hadamard product. It's the component-wise multiplication as opposed to the proper polynomial multiplication. So like X stuff times X stuff, Y stuff times Y stuff, Z stuff times Z stuff. And you can show that pushing through the powers of A as you go, and then the X from the front end, you can show that this ends up picking up all possible monomials, meaning all the cross terms, quadratic in the X's as they're read in. So it's straightforward to show. It just takes a bunch of algebraic steps. It takes a lot of time. So this is easy to prove. That's in that long paper of mine. But anyway, when you do that, and then you train on the R's and then powers of R, then this is just through quadratic. You end up picking up a model that has all quadratic monomials of X as well as all linear monomials of X. And that ends up being equivalent to not just the var I just showed you, but the quadratic terms as well. So I call that NVAR for nonlinear quadratic var. And if I did cubic terms here, R circle, R circle, R circle, R, and so forth, it would pick up all cubic monomials. And it's clear that counting monomials grows quickly. So if you actually want to form this matrix, it's ugly. It's ugly to write out, but it's very easy to do. So anyway, just think an NVAR. An NVAR like this is equivalent to a well-working, fully trained linear reservoir with nonlinear readout. So you can do either one. It's the same thing. And that's eventually what we did, Dan Gothier and I, in this paper, is we just thought of an efficient way to do what I just told you, without having to think about forming all the cross terms. Okay. So we call this next generation reservoir computing because we're never actually picking random matrices. We're just going straight to the NVAR variation of it. And this is a cute operation, which is kind of hidden in our paper, that picks up all quadratic, cubic, quartic monomial terms. Okay, so this is written as a feature vector on several delays. If you want to feed in the time delays directly, he calls them taps. Then the nonlinear terms would be this operator. What is this operator? That is the Kronecker product between matrices or vectors. And then this little operation I thought of, writing a notation for it, this half bracket above it just says, pick out the unique terms. So actually, like, again, if you're speaking MATLAB, it's very easy to do, because just Kronecker two vectors, and you just wrap a unique around it, and it picks them out quickly. So that's not a computationally efficient way, but it's a very easy programming way to do it. And it's not computationally too expensive if you're doing it at each step before you build too many terms. So anyway, you do that thing, and you can build a big array of readout terms, and then build a fitting term and fit your nvar. So this is the whole process in a step, but at this stage you can kind of guess what it is. It's a lot like I did before, but with this cute operation. It works fantastically well, but since I have very little time yet, I'm super slow, I want to go to something that I haven't talked about at all, and so it's kind of half-baked, but ready to go. So a different machine learning paradigm that's random is called extreme learning machines, where you don't have the recurrence in them, or the recurrent net. It's simply a feed-forward neural net where you choose the weights randomly and only the readout do you train. So it's very much like a reservoir computer, but with no recurrence in it. And if you're going to feed in a vector of data with delays, like Luke talked about a bit this morning, I was driving, I heard him. You're essentially saying, hey, Tokens embedding, please take care of that part for me. Pick up the memory for me, make your delays big enough, feed in that guy. And then a feed-forward neural network may be able to handle the job. And sure enough, you can do this kind of thing with a fully trained feed-forward neural net, and it does an okay job of forecasting. I'm kind of playing around with this for reasons of explaining some things, but there's one feature I want to show you. It's a pretty picture I want to get to at the end. And believe it or not, I can do it in 2 minutes. Anyway, all this says is do a feed-forward neural network, no recurrent loops. And if you have several layers, call it deep. If you just have the original Elm extreme learning machine had a single layer. Either way, it's a similar concept. And you do composition with a threshold function, but now I'm actually going to choose a specific threshold function. Ignore what I said right there. That's a typo. I want to, this is what I want to show you. It's the ReLU function. I'm going to choose the ReLU function because it's easy to show a very beautiful picture. And then you fit just the readout by ridge regression. So a ReLU function in 2 dimensions essentially is a ramp, and the threshold where you get equal 0 is a line in 2 dimensions. And in multi-dimensions, it's a hyperplane, but I'm drawing 2 dimensions because it's easy to draw 2 dimensions. So each one ReLU is essentially a ramping function with a zeroth part and a ramping part. And then if I'm adding, if I read in data, say 2-dimensional data into such a neural net, and then this is the value on each node that is a ReLU function, then on the readout phase, I'm essentially taking a linear combination of those, and I have the number of domains in terms of the number of overlapping regions. So this makes a classic problem in like ancient problem in toy geometry. I learned as an undergrad. How many regions can n lines in the plane, n randomly dropped lines in the plane form? And that's a well-formed problem. I forgot the formula, but I have it written here. So anyway, it's just piecewise linear functions in these domains, and that's kind of a cartoon of it. So this is the counting in d dimensions, d0 dimensions, n hyperplanes. This is the number of piecewise linear domains. Bounded domains is smaller. I'm going to go to, here's a deep picture of the same thing, a deep neural net. Here's many. And so as it gets large, you get smaller and smaller domains, and this is driving after something they call expressive in neural net community. How expressive is your problem? And even these neural nets are quite expressive, and you're taking you're taking trained projections from these expressive but otherwise piecewise linear and continuous functions onto your specific function set. So that's my last slide. Forecasting with the Elm works okay. It's not beating the Reservoir by any means, but it's actually working okay. I'm not trying to beat it, I'm just trying to understand it. And this kind of story about random projections from partitions of the plane and hyperplanes was kind of interesting to me. And it might do better with some better understanding of what goes on, but anyway, it works okay. So this is trained on the same Losody-Mackey. By not okay, it means it doesn't go as far out in the number of Lyapunov times. I better stop there because of my moderator, he's scary.
All right, let's thank our speaker.